When I asked you yesterday, what's the Earth like inside? Guys? You guys gave me 4 or 5 answers, and they were all good. You said there's layers. You said it's really hot, it's really dense, there's a lot of pressure. Those are the big ideas. So let's start off with the heat. All right? And the first question that you'd have to ask, why so hot? All right? Why would the Earth be so hot? Anybody wonder that? Yeah, it's a good question. The answer is because there's kind of like a 1,000-mile across ball of nuclear power inside the Earth. Right? And that's how we're going to think about it. Inside the Earth, the core of the Earth, this part right here. Hey, cool. This part right here, very center, that's made up of metals. Right? And most of the metals, the most common metals in there are iron and then nickel. But there's also quite a bit of uranium. And when I say quite a bit, less than 1%, but enough that it actually adds up. And you remember what uranium does? Decomposes. It's radioactive so that it decays. It turns into other stuff. Basically, it falls apart. And when it falls apart, it gives off just huge amounts of energy, right? That's how a nuclear bomb can create such a big explosion. Have you guys seen nuclear bombs? The actual amount of fuel that's burned up during a nuclear explosion is tiny. It would easily fit inside this box with a lot of space left over, right? To give you one of those big old mushroom clouds and those explosions that can, level entire cities. Nuclear power is that powerful. So inside the Earth, you've got a bunch of that uranium blasting itself apart and giving off huge amounts of energy. That's how the Earth stays so hot. The other thing that helps the inside of the Earth stay hot is the crust. Right? Is the outside of the crust hot? No, we're standing on it. Right? So it really works like a blanket. It traps the heat inside, instead of that heat just radiating off into space. So that's going to be important because so much of what goes on inside the Earth is due to the heat and the pressure. You got a question, Jackson? Well, that's what we just talked about, right? Because basically, the crust works like a big blanket on top of the Earth. Right? So that traps the heat in, which makes it cool for us on the outside.
So is that why it's so hot near volcanoes?
Yeah, a hole in the blanket. You can think of it that way. Yeah. Very little. I mean, not really. Compared to how much heat we get from the sun, the amount that actually leaks through the crust to us is really small. And if you don't believe me, go to Antarctica, right, where they don't have the sun. There's not much heat coming through the crust to warm up Antarctica, right? But yeah, some. If the sun went away, you'd be able to measure small amounts. All right, cool. So the next thing we need to look at, and this is stuff that you kind of already know, you should already know. This came up in our discussion last time. There's some patterns that you notice as you go deeper and deeper into the Earth. All right, number one, it gets hotter. And if you think about what's going on inside the Earth, where was that ball of nuclear fuel located? Located at the center, right? So that explains why it's going to get hotter as you go towards the center, right? That's where the heat source is. Pressure is also a factor. Right? The more pressure creates more heat, too. But we don't really need to look any further than the heat source being at the center. Right? So as you get down closer to it, it gets hotter. There's more pressure as you go closer. Why would that be? You guys think I keep these physics books around just to look cool. Everybody looks cool when they have a stack of physics books in their hand, right? If I were to take a physics book, and set it on my hand, this creates some pressure, right? Doesn't it make some pressure on my hand? What if I add a second physics book on top of that? What happens to the pressure? More and more and more. Well, that's just adding, this is quite a bit of weight, right? It makes quite a bit of pressure. That's just adding 4 physics books. As we go down deeper and deeper into the Earth, there's more and more Earth stacked up on top of us. In fact, by the time you get down to the center of the Earth, there's about 6,000 kilometers of Earth stacked up on top of you. That's like a lot or something, right? In the neighborhood of 4,000 miles. Not that we use miles because this is a science class, but yes, sir.
Wouldn't the heat inside the Earth create like a vacuum?
No. Yeah.
If the radioactive material like had timed out, like ran out, would it still be hot?
No. And there will be at some point. You're right. The Earth will have burned through most of its radioactive fuel, and the core of the Earth will actually solidify. On smaller planets, that happens really fast, right? That's why the moon's solid. Here's the good thing, though, guys. Hang on. The thing is, most of this is uranium. Do you remember uranium's half-life? It was about the age of the Earth, right? 4.5 billion years. So it's going to be a little while. I'll go ahead and leave it there. It's going to be a little while before any of this happens. Yeah?
And we'll be dead by then because the sun would have turned into a red diamond.
Yeah, exactly. So, but at some point, yes, the Earth will run out of heat source and it will cool and solidify. One more question, yeah? We're going to talk about that. The heat inside the Earth is really important. It explains some really important stuff. And I'm only not answering that now because we're going to come back around to it in today's lesson. So the next question that you guys should have wondered, or maybe you already read the answer to this, is, right? Was anyone wondering, right? How do you know what's going on inside the Earth? Right? Like anyone could ever know that. The main way we know that, they're called seismic waves. It's by studying earthquakes. Right? And looking at the way waves travel through the Earth. The details of this can get kind of confusing. I'm not worried about the details. We're just going to talk about the big idea. Guys, shh. The big idea is this. The big idea is that we know a couple things. Number one, we know that as waves, and actually I'm not going to draw it because it's on the next slide. We know how waves act when they travel through things. So the next slide is going to talk about that. I'm kind of getting ahead of myself. Erase that. There's two different kinds of waves. These ones are P waves. And when you think about P waves, there's two P words you should think of. Pressure and primary. Right? Usually they're called primary waves, but P waves are pressure waves. And they're called primary waves because what does primary mean?
Main.
It could mean your main one or your first one, right? So primary waves come first. Let me show you a little bit about these primary and secondary waves with my pal Slink here. So, let's see, where's a good spot? This might be the best spot. What I'm going to do is I'm just going to hook one end of the slinky to something, I hope, it doesn't move. That'll do it. Then I'm going to stretch it out. Hopefully you can see this a little bit. You may need to stand up if you're a long ways away from it. But there's two different kinds of waves. P waves or pressure waves work like this. Right? See how if I take one and I compress it, you can see a wave traveling back and forth in the string, right? It's a pressure wave. Notice the slinky itself doesn't move anywhere. If you keep your eye on one spot on the slinky, it never moves, or at least never moves much. It shakes a little bit and comes back. But you can still see the energy traveling through that pressure wave, the primary wave, right? Well, P waves can travel through anything. In fact, they're traveling through the air right now. That's how you're hearing my voice. When you listen, yeah, thank you. I thought it was a nice voice. When you listen to music or when you hear a sound, that's a P wave or a pressure wave traveling through the air. My vocal cords are, think of a speaker. You know how a speaker goes, you can see the speaker moving? It's just bumping the air. It's doing exactly what I'm doing here. It's going, bah! Right? except it's doing it to the air and sending a pressure wave through the air. So pressure waves travel through anything. Write that down. P waves travel through anything. They don't travel through empty space, but that's nothing. They don't travel through nothing, they travel through anything. Then there's S waves. Right, those are the other ones, and I have a feeling these ramps are going to get in the way a little bit. Speed as much as I can. But S wave means secondary wave, or it means shear wave. Shear is a word that probably you guys don't use except for talking about trimming a sheep's fur. But here's a shear wave, right? It's different. Watch. You could do it up and down too. This link is not really strong enough. Yeah, there we go. There's a shear wave. Or an S wave. Two things about this wave that you need to know. They travel slower. That's why they're secondary waves. S wave stands for secondary wave. They get there second. Be fine there for now. S wave stands for secondary because they get there second, and it stands for shear wave, which just tells you it moves a different direction. Light waves travel like that. And it's different than sound. But light waves travel through the air up and down like that. So these, and here's just two still pictures of P waves versus S waves. What's up?
So they travel slower and what?
They can't go through water.
X wave, yeah, you could even think of S as slow, but they're called usually secondary waves. And S waves cannot travel through water. Or liquids. Sorry, I shouldn't say water. Yes?
Aren't ocean waves like S waves though?
I knew that was going to happen. There's a third kind of, no, they're not. They look like it, right? Because the surface of the water looks like this. That's true. But they're not actually S waves. They are a complicated surface interaction.
Okay.
And the best way I can tell you that they're not an S wave is notice that when you do an S wave, it travels underneath. If you are in the water just below the surface, as a wave goes over your head, you don't notice it, right?
Unless you that's okay.
Okay.
Happens pretty often.
Well, sure, but if you're down here, you wouldn't notice it.
Okay.
You're right. Yeah.
Since P waves are like talking, if you're in water and you know how you can,
Yeah.
but it's like super muffled,
Right.
why can't we hear it like clearly
If it can go through the water.
Hey.
if it can go through water?
Megan. Come on. The best reason for that is because waves travel differently in different materials. And your ears are tuned to hear things in the air. Yeah.
If ocean waves traveled like S waves, would the current be much stronger?
That's a good question. Maybe. I'm not sure. Never thought about that. All right. So here's the deal. When we put P waves and S waves together, you remember seeing pictures like this when you read stuff or when you looked online yesterday? It's a little bit confusing. I'm not going to make you get into the details of this. But here's what you do need to know. And you're actually going to have to explain in writing how we can use waves to figure out the layers of the Earth. So this is a tough question. The basic answer is this. First of all, I know the answer. I'm just trying to think of how to explain it. Now, the main thing that we do is we have detectors set up everywhere. So if there's an earthquake right here, we're going to detect, we have meters all over the Earth's surface that are going to detect the same earthquake. And those detectors can detect P waves and they can detect S waves.
The time it gets there?
And they can detect when it gets there. And there's actually a third kind of wave that travels just through the crust of the Earth. That's more like an ocean wave. But don't worry about that right now. That's not playing in here. So what we do is we can detect how long it takes them to get there, and we know whether they were traveling through, we can detect how long it takes to get there, and we know the difference between P waves and S waves. So one of the tricks that we use is if we're standing right here, we get a P wave, and then 2 minutes later the S waves come through, then we can figure out how far away the earthquake was. The main way we figure out the layers, though, is by looking here. Look at that. You remember reading about this? It's called the shadow zone. Sounds mysterious, right? The shadow zone is where you get no waves. None at all, Fred. And that's the reason for that is because the P waves, the pressure waves, can't travel through a liquid. Right? So when they get to the core of the Earth, right, it turns out the outer core is a liquid. So when they get there, that eats up all of the S waves.
You said
P waves can't
Give me
travel.
a second here. So if you're all through this range right here, all through this entire range right here, you're going to get no S waves whatsoever. Right? And the reason for that is because the liquid core is blocking out all those S waves. All right? One more thought. You also get a shadow zone here from P waves, because P waves they can go through a liquid, but they bend when they get to the core. So that's why if you look at these pictures that you've seen, it's coming in, the wave's coming in like that, and whoop, it bends and goes like that. And it turns out that waves bend when they get to new materials too.
yeah.
Just like if you put your hand underwater, it looks like your hand's
There's
broken.
no like fraction.
So, who had a question? Somebody had their hand up. Yes.
First of all, you said P waves
Yeah, I know.
can't travel through liquid.
Did I say that?
Yes.
Bad me.
Okay.
And how could a epicenter in like the shadow zone ever detect earthquake?
You mean if you're standing here, could you detect an earthquake there?
Yeah.
Yes, but you wouldn't get P waves or S waves. You would get the third type of wave, which is a surface wave, which would travel just through the crust. Uh-oh, now I'm in trouble. What's up, Matt?
Would it take much longer to get around that way?
Yes.
So like, I know this is like weird question, but like, why do we care? Like,
Okay. Wow. I'm going to pretend for the moment that you meant that in a good way.
I did.
And then we'll get back to, and someone else, I think it was Jasmine, was asking this earlier too. This is out of order, but here's why you care. You'd be dead without it. Right? And the surface of the earth would be without mountains or rivers or valleys. It'd be completely formless. So the two ways that these liquid layers of the earth, right, and that's what I was trying to tell you, we can figure out that the earth has liquid layers. The reason why we care is two reasons. Number one, those liquids allow the continents to float around. Have you heard of continental drift or plate tectonics theories? The plates on the earth are moving around. Because you don't want to be an idiot. That's why. All right? All right. That's reason number one. Reason number two is, and those come from a liquid layer in the mantle. It's called the asthenosphere. We'll talk about it in a second. There's a liquid layer in the core of the Earth. Remember we talked about the outer core is liquid? And that gives the Earth a magnetic field. The magnetic field traps particles that would kill us. Worse than UV radiation. There are charged protons and electrons and positrons and antiprotons and some weirder stuff too. Blasting through space at the speed of light, and they'd be devastating to living things, but our magnetic field traps them. Gives us the northern lights and the southern lights too, when those charged particles get trapped. So there's the quick answer to why those liquid layers matter. Yeah?
So, it was something that, like, the northern part of the earth, like, on top of it, break the magnetic field of the Earth?
Harder, actually. And a rocket wouldn't really be affected by the magnetic field of the Earth. But the magnetic field is stronger near the poles. So the closer you get to the poles, the stronger it is. That's why those northern lights that we were talking about only happen in the north and in the south. They're not called the northern lights in the south. Yeah?
Is there, like I've heard that there's rare occurrences when you can see them, like from here, is that true?
Yeah. Yeah, and it is rare. The reason is because our magnetic field is weaker here, but not zero. Right? We still have a magnetic field here. So we would only see it here when the conditions were just right and the sun was really acting up and shooting a bunch of particles at us. The sun goes through weather, kind of like the Earth does. When it acts up, it sends more particles. Caleb?
Does the magnetic field only affect P waves?
Only affect what?
P waves? Or does it affect all waves?
The magnetic field is affected, it affects charged particles. So anything that has an electric charge and is moving. Yes?
So would anything happen to like our magnetic field if there was like a big enough earthquake that was like shaking our core? Because you said that P waves travel through the core, and the core is made of metals, which causes our, I guess you could say our magnetic field. Would anything happen to our magnetic field if an earthquake was big enough?
I don't think so.
Wait, since the P waves travel through to the inner core, and the inner core is solid, doesn't that mean that the inner core would have like mountains on it?
Would it?
Inner core would have. Not necessarily. Let's get back in order here, guys, and we'll come back and tie this together. So we'll come back around and we'll explain that a little bit more. One of the things that you're definitely going to have to do, and like I said, I got rid of all the unimportant stuff, so every slide has important information on it. But you're going to have to name 8 different parts of the Earth. These are the 8. Yeah.
So this might seem stupid, and I should probably know, but why does it alternate between solid and liquid? Is that just because of the composition of the materials, or?
Yeah. Okay, that's complicated, and I'll get to that. It's a good question. So there's 2 different ways, and this confused me for a long time. When we're naming the layers of the Earth, there's 2 different ways to name it. That's why these layers overlap with each other a little bit. Sometimes the layers on this side overlap with the layers on this side. So it's not like there's 8 separate layers. There's actually 2 different ways to break it up into layers. If you just look at what the Earth is made out of, that's on the right-hand side here. You'd notice 3 different major changes. All right, the first thing that happens is you notice the crust. And that's very thin. This is the crust right here. The crust is made up of rocks like we know them. Granite mostly. Basalt. Whatever that may be.
I love that stuff.
Yes. So the crust is very thin, but if you go just a little bit beneath the crust, and we're only talking going a few miles, right? 10 to maybe 25 kilometers. If you go just a little bit beneath the surface, you'd notice that it changed materials. That all of a sudden it was made up of silica-type materials, which are still related to rocks, but it's a different form of rock. And these materials would go quite a ways into the Earth. They would go a few thousand kilometers into the Earth. So this part would be really big. And then when you got to the core of the Earth, maybe halfway to the center of the Earth, you'd notice that things turned into metal. So the core is made up of metals, mostly iron and nickel. And if you want one-word answers for this stuff, the crust is made up of rock as we know it. The mantle is made up, I guess you could say, magma. And the core is made up of metal.
All right, Dr. Egan.
Yes, indeed. So, where does the solid-liquid thing come in was a question that you guys asked. The short answer is, if you just look at the mantle, there's solid and liquid parts of that. If you just look at the core, there's solid and liquid parts of that. So the deal is, the reason is because you have two things that are fighting against each other. Right? You have pressure versus, it's kind of like Superman versus Batman. Did you guys see that movie?
Yes, I like it.
Pressure versus temperature.
I didn't see it.
Okay, guys, as you go deeper down into the earth, both of these things increase. But here's the problem. As the pressure goes up, pressure wants things to become solid. Right? When you increase pressure, usually things are more likely to become solids than liquids. When you increase the temperature, you know what happens to things, they melt, right? So these things are locked in an epic death battle, an epic death match. As you go down into the earth, who's going to win? Does the pressure win and make things become more solid, or does the temperature win and make things become more liquid? It trades off. All right? So going back to this, what happens is, of course, you know the surface of the earth, the lithosphere, is a solid. But as you go deeper down into the earth, it becomes liquid because of the increase in heat. Right? There's enough pressure, or there's enough heat, I should say, not pressure. There's enough heat that for the asthenosphere, things are liquid. And the asthenosphere is this part right here. In our picture, it's orange. The lithosphere actually covers the crust and the upper part of the mantle, but it's the solid stuff. So it looks, as we go down, when we go from the lithosphere, which is solid, to the asthenosphere, which is liquid, it looks like, aha, heat wins. Right? Because as you go down, it becomes more liquid. But when you get to the mesosphere, it actually changes. You get so much pressure that even though it's super hot, the rock does not act liquid anymore. It becomes solid. Yeah, Matt.
By comparison, when an earthquake happens, how much of the pressure is released versus all of it on the earth?
It depends on the earthquake. But during a big earthquake, all of the energy can be released.
What?
All right. So we go solid, but it gets hotter, so it turns into a liquid, and it wants to stay liquid, but there's so much pressure as you go down deeper that causes it to be solid. And then finally, we get to the core. Right? And the same thing happens all over again at the core. At the core, it's super hot, but remember, the core is new stuff. The core is now metal, right, JJ? So that means that metals are going to act differently than the rocks did. Metals can still be liquid here for the outer core. So the outer core is a liquid metal. But same thing happens. It looks like temperature is going to win until the pressure gets super freaky mega crazy. And for the inner core, things go back to being solid again because of the pressure. So the reason it goes solid, liquid, solid, liquid, solid is because of that battle between pressure and temperature. Last idea here, guys. And we started to talk about this when Grant asked his question, "Why are you making me do this?"
No.
He didn't sound like that. I sounded like that. But convection currents are key. Have you seen that word, convection? Convection current is just what it says. It's a current in a liquid or a gas. They can happen in the air too. But usually they're in a liquid. And what happens is stuff gets hot. What happens to hot stuff? Think of a hot air balloon. Yeah, when it gets hot, heat rises. You've heard that before, right? If you like slept up in a loft in the summertime, it can be cool down below, but it's hot up top. Heat rises. So that's what causes convection currents. Take a look. All right, I'm trying to be quick, but I need you guys' attention. The heat. This is a pot of water on the stove. It's a great way to learn about convection currents. This is the Earth, and you'll see that they're actually doing the exact same thing. For both of them, there's a heat source on the bottom, right? The pot of water is sitting on the stove burner, and what's the heat source, or should I say, where is the heat source in the Earth? It's the core, right? It's on bottom. So the heat starts right here. The stuff on bottom gets hottest. And when it gets hot, remember what heat wants to do? Heat wants to rise, so it comes to the top. But when it does that, you can't have nothing at the bottom, so something needs to take its place, and what takes its place is cooler stuff from the top. Right? You see the same thing when you boil your spaghetti. Right? Why does it go all bubbly and churny? It's convection. It's because the heat at the bottom is trying to get to the top, and the stuff at top has to go down and fill in for it when it goes up. So you get that. Marion, what's up?
I was gonna say, like, why would it, like, travel through the solid?
Right. Okay, you're right. What happens is the heat happens down here in the core. And I think what you're saying is that, wait a minute, there's this solid layer in between the core and this layer. Is that what you're getting at? Saying, well, how does the heat get there? Slowly is the answer. Right? The heat has to work its way through here through a process called conduction, which is kind of like
When, like, you have, like, a metal thing next to, like, in the fire, right?
yeah. If I took like a spoon or something and I stuck it in the fire,
You would drop it because it would
eventually I would drop it because the heat would conduct itself up through the spoon handle into my hand, right? It would eventually pass through the spoon into my hand. That's how the heat conducts itself through anybody remember what this is called?
Yeah.
You're going to need to.
That's so sweet.
And then it gets up to the, what's this one called? Asthenosphere. And when it gets to the asthenosphere is, can I be honest with you guys? Liquid's not the best word for it, but it behaves like a liquid in that you can have convection. So we're going to call it a liquid to simplify our thoughts.
It's like it's kind of like oil, like a little bit thicker than water.
It's more like silly putty. Would be the best way to think about it. But we're going to call it a liquid to simplify our lives. All right, so these convection currents, last thing I'm going to say, if I take a block of something that floats and I set it on top of this, do those blocks hold still?
No.
They get pushed around. That's why the continents move around, giving us mountains and valleys and earthquakes and volcanoes. And the brilliant cinematic masterpiece, San Andreas. Yeah.
And that's why, but you said, since you said it takes a long time, that's why it takes so long for the continents to move. Correct?
Yeah. Does that make sense, Delaney? Yes, sir. Remove your hand.
What I was going to say was, since earthquakes occur by energy pushing, plates pushing together, and then they either push under or up.
Yeah.
Then doesn't that mean with like mountains, since they form by going up, doesn't that mean that when another earthquake happens on them, they'll just get bigger?
Usually. Right, and like there's, yeah, definitely. All right, so we talked about this, but the things that you need to know, and this one will take just a couple seconds if you guys can tune in with me. The continents float around on the asthenosphere the same way that these wooden blocks float around on the top of boiling water. They get pushed around. So if you look at this, here we are in North America. We are actually moving towards Japan at a very exciting, 10, 15 centimeters per year. So it'll be a while before we get there. But we're moving. And it looks like, if I look at this picture, like the Eurasian plate, which has Japan, is actually moving towards us, too. So hey, double the speed. So anyway, we're going to talk a lot more about this in the second half of this chapter. This we're just going to mention, but it's really important to know about. The Earth would not have a magnetic field if it wasn't for the liquid outer core. Yeah.
So does that also mean if we didn't, if it like, I don't know, like we didn't have anything in the middle anymore, like the radioactive material died out, does that also mean that
our moon would fly out of our orbit because we wouldn't have, no?
No, gravity would still be around even without the magnetic field. Gravity and magnetism are two totally separate things. There's 5 different fundamental forces of nature: electricity, magnetism, nuclear strong, nuclear weak, and gravity. To us, as far as we're concerned, they have nothing to do with each other. To a cutting edge physicist, maybe not. But. All right, guys. That concludes.